Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today, we're doing a deep dive into the solenoid. It's a really fundamental topic from Unit 4, moving charges and magnetism. And our goal is simple, really. We're going to make this so clear that you'll remember it for life and, of course, score full marks. So to start, let's think about something you've probably seen. You know those huge cranes in a junkyard? The ones with a massive magnet? They lift these giant piles of scrap metal. But here's the interesting part. How do they just switch the magnet on an N to lift everything and then just switch it OFF to drop it?
Oh, that's a good point. A normal bar magnet is always on, isn't it? You can't just turn it off.
Exactly. You hear it.
So to have that much magnetic force and to control it instantly, that must be something completely different. It has to be electric.
It is. And that something different is the solenoid. That's the technology hiding inside those massive electromagnets. But it's not just for junkyards. Think about MRI machines in hospitals. They need incredibly strong and very stable magnetic fields. We're talking 1 to 3 Tesla. That's a huge amount.
Why? Okay.
That's a solenoid. Or even something like a fusion reactor, where they have to contain plasma that's millions of degrees hot.
They use magnets for that.
They use a magnetic field created by solenoids to hold it. So a simple coiled wire is doing all of this. We need to understand how. Okay, so let's break down the basic idea. What is a solenoid? At its core, it's just a long wire wound into a tight spiral, like a spring, a helix.
Right.
When current flows through it, each little turn of the wire acts like a tiny circular loop. And we know a current loop is basically a small magnet, a magnetic dipole.
Okay, so you have hundreds of these tiny magnets all lined up.
Exactly.
Yeah.
And when you stack them so close together, their fields combine. And this is the magic part. They create a very strong and very uniform magnetic field inside the coil.
And outside.
And almost zero field outside. That's the key.
But how? How does stacking them make the field so neat and tidy inside and just disappear outside? Why doesn't it just spread out everywhere?
Perfect question. Let's use an analogy. Forget the wire for a second. Imagine you have a lot of small, weak bar magnets. And you stack them end to end, north pole to south pole, north to south, again and again to make one long cylinder.
I can picture that.
Now, what would the magnetic field look like inside that cylinder? All the individual fields are pointing in the same direction, from the overall north to the overall south. They add up.
So it'd be strong and all the field lines would be parallel. Uniform.
Exactly. Strong and uniform. Now, what about outside the stack?
The north pole of one magnet is right next to the south pole of its neighbor.
Yes. They are so close that their external fields just loop around and cancel each other out. So you get this confinement. The field is trapped inside. That's why this geometry is so useful.
I see. The geometry is what confines the field. But the crane can be switched on and off. A stack of bar magnets is permanent.
Good catch. The analogy explains the shape and strength of the field. The controllability comes from the fact that our solenoid's field is created by an electric current.
No current, no magnetism.
No current, no field. Simple as that. So let's build a mental picture. Imagine a long tube wrapped super tightly with a glowing copper wire.
Okay.
Inside that tube, just see dense, straight, parallel red lines running right along the axis. That's your uniform field. And outside, almost nothing. Just a few faint lines curving around the ends. That confinement is everything. All right, now that we have the feel for it, let's get into the formal, exam-safe language from NSERT. The textbook is very specific about what an ideal solenoid is. Could you read the definition for us?
Sure. NSERT says, by long solenoid, we mean that the solenoid's length is large compared to its radius. It consists of a long wire wound in the form of a helix where the neighboring turns are closely spaced. So each turn can be regarded as a circular loop. The net magnetic field is the vector sum of the fields due to all the turns.
Perfect. That first line is the key condition, isn't it? Length is large compared to its radius. That's what makes the field outside basically zero. Now, for the calculation, if we had to add up the field from every single one of those hundreds of loops using the Biot-Savart law, it would be, well, impossible in an exam.
It would take forever.
It would. But because of the solenoid's beautiful symmetry, we can use a much simpler tool, Ampere's circuital law.
Okay, so the formula we get is simple. But the real trick is knowing why we're allowed to use Ampere's law here.
That is the crucial insight. We imagine a rectangular loop. Let's call it ABCD. We place it so one long side, AB, is inside the solenoid and the other side, CD, is outside.
Right.
Ampere's law looks at the magnetic field along all 4 sides of this loop. Now think about the side CD, which is outside.
Well, we just said the field outside is nearly zero for a long solenoid.
So the contribution from that side is 0, gone. Now, what about the two short sides, BC and add? They are perpendicular to the field lines inside.
Oh, and the dot product, B.dl, has a Canese 90 in it, and cos 90 is 0.
So they are also 0. 3 out of 4 sides contribute nothing at all.
Wow. Okay, so only the part of the loop that's inside and parallel to the field matters.
That's it. And this incredible simplification gives us our final beautiful formula for the magnetic field inside the solenoid. B equals mu naught Ni. And we have to be very, very careful about what N is. It's not the total number of turns. It is the number of turns per unit length. So N equals capital N divided by L.
Wait, so if the formula is B equals ENI, then the density of the winding is what matters most. I could have a very long solenoid with 1,000 turns, and it might be weaker than a short one with only 500 turns if the short one is packed much tighter.
You've got it. That is the single most important concept here. It's all about packing density N, not the total number of turns. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com. Okay, let's immediately use this formula. We'll take the classic worked example, 4.8, from the textbook. So we have a solenoid. Its length, L, is 0.5 meters.
Half a meter.
And it has 500 total turns, N. The current I is 5 amperes. So what's the field inside?
Okay, so first step is to find the turn density, little n.
Yes. What would that be?
That'd be n divided by L. So 500 turns divided by 0.5 meters. That's 1,000 turns per meter.
Excellent. That's a good density. Now for step 2, we just plug everything into our formula. B equals 4a10 times 1,000 times 5.
Right, so that's 5,000 times 4a10a, which comes out to be 6.28 10 to 11.
Or 6.28 millitesla.
Exactly.
Well, wait, a minute ago you said MRI machines need 1 to 3 Tesla. Our result is in millitesla. That's hundreds of times weaker. How do they get such strong fields then?
That's a brilliant question, and it connects directly to what we'll study in the next unit. What we just calculated is for an air core solenoid, there's just air or vacuum inside.
Okay.
The secret ingredient is putting a material inside. If you place a soft iron core inside this coil, the magnetic field gets amplified enormously.
The iron boosts the field massively. By a factor of hundreds, even thousands. That's the trick used in all-powerful industrial electromagnets. But that's a story for the next chapter. Now let's talk about the silent killers. These are the small mistakes that can cost you big marks in the exam. Misconception number 1 is about the outside field. A lot of students think the field outside a solenoid is just weaker than the inside, like a bar magnet.
I can see why they think that, but it's wrong, because the whole point of the solenoid's geometry is confinement, right? The fields from neighboring loops cancel each other out on the outside.
Precisely. So the correct idea is, for a long solenoid, the outside field is nearly 0. Remember, solenoid field is all inside, almost none outside.
Got it. All inside.
Okay, misconception 2, total turns versus density. It's so easy to think that more total turns, capital N, always means a stronger field.
But we just saw from the formula that's not true. It's N, the turns per unit length. So the correct idea is that the packing matters. A short, tight coil is better than a long, loose one.
You've got it. Remember that. Always calculate N first. And the last one, number 3, the effect of the iron core. Some students write that putting an iron core inside has no major effect.
Which we just learned is completely wrong.
Yeah.
That's the secret to making the field super strong for things like an MRI.
Right. The iron core gives the field a mega boost. So remember, practical electromagnets always use iron.
Okay, those are 3 really good points to remember.
Now, to make sure this all sticks, let's create a few memory anchors. First, the formula itself, B, U, is mu Ni. It's easy to say, just say it like it sounds. Mu naught Ni.
Mu naught Ni.
Simple enough. And for the direction, we can use a physical gesture. The right-hand rule works perfectly.
Oh yeah, so you curl the fingers of your right hand in the direction the current is flowing around the coil.
And what does your thumb do?
Your thumb points straight along the axis, and that's the direction of the magnetic field inside.
Perfect. It's a great way to instantly know the field's direction. And finally, a little association. Think of the solenoid as a magnetic bottle.
A magnetic bottle.
Yes. It traps the magnetic field inside. And you need the right current, I, and tight winding N to put the cap on the bottle properly so the field doesn't leak out.
I like that. A magnetic bottle.
All right, so let's summarize with 3 short exam-safe points. 1, the magnetic field inside a long solenoid is strong, uniform, and points along the axis of the solenoid. 2, its strength depends on the current, I, and the turn density, N. The formula is B equals E-N-I. And 3, the magnetic field outside an ideal long solenoid is nearly 0. This confinement is what makes it so useful. To get maximum marks in 12th CBSE physics, chemistry, and maths, visit profsam.com.
That is PROF Sam, right?
Yes, exactly. PROFSAM.com. Keep practicing with the formula and remember the core ideas of confinement and density. Study well, and we'll see you in the next deep dive.